Hello. So this is your course instructor, Khushwant Fatnani. Let's start off with the session. Today we'll be doing properties of solids and liquids, that is properties of matter. And in the next class, we'll be doing more practice questions based on it. So let's start off with the session. All right, let's begin. So the topic name is properties of matter, right? Properties of matter. And this includes both solids and liquids, all right? So we are doing the unit properties of matter. So as it's a revision class, right, we'll try to cover as many important topics as we can, right? In case there are any other queries that you have, feel free to forward them to me, right? You can either put me a message or you can also mail me at physicswithfatnani@gmail.com, right? So this is the heading properties of matter, or you can call them properties of solids and liquids, right? In particular, we are reading about solids and liquids. All right, so let's begin. Okay, so let's start off with few important topics in the chapter, right? And how many marks distribution is there every year that you can see in the paper, right? So let me tell you first of all about the mark distribution which comes from this chapter, right? Marks distribution which comes from this chapter. So every year there is a possibility that from this entire chapter you may find sometimes one question, sometimes even four questions, right? Sometimes even three questions. So let's take an average of, let's say, four questions, right? Let's take around 3 to 4 questions are asked every year in your papers, right? JEE mains, and you talk about NEET, which are based upon this chapter, right? So let's take around 3 to 4 questions. Now, this distribution may vary from one year to another. Some year it may be one question, some year it may be even four questions. But yes, you will always find at least one question from this chapter. So let's take this around 2 to 3 questions every year from this chapter will be present, right? From this unit will be present in your uh, exams, right? Whether you talk about JEE or NEET. Now, let us take the syllabus part, right? So, what about the syllabus of this chapter? So, the main or the important topics that we are going to study from this chapter are first, elastic behavior, right? The elastic behavior of matter. Then we are going to look at what is stress and strain in terms of solids, liquids, and gases, right? Stress and strain. There is a relation called as Hooke's law. There is a relation called as Hooke's law. We also have the concept of work done or the potential energy in a stretched or in a stretched wire, right? So we have work done, right? Or either you can call it work done, or you can call this as potential energy. Work done in stretching a wire, or potential energy in a stretched wire, right? In case of a stretched wire. right? So this is next. After this, you will have a topic called as thermal stress and strain, which means how because of heat, stress and strain can be introduced. Thermal, of course, means heat, right? So you have thermal, stress, and strain. Correct? Now, then we are introduced to a topic called as viscosity. So this is revision class, right? So we'll be seeing a quick meaning, right? And in case there is any doubt, just forward it to me in the class itself so that we can discuss them, right? Then we will read about different kind of flows, right? So the kind of flows that we'll read about are streamline and turbulent flow. Streamline and turbulent flow, right? Then you have something called as equation of continuity. Super important. Equation of continuity, right? Next one is Bernoulli's theorem. Next one is Bernoulli's theorem. Then comes the concept of surface tension. Concept of surface tension. Correct? Then comes the concept of surface energy. Of course, these two are very intriguingly connected, right? Very intricately connected, woven into one another, right? So without surface energy, there is no surface tension. Without surface tension, there is no surface energy. Then we also see the concept of angle of contact, right? Post which we see the concept of capillarity or capillary rise, a very beautiful phenomena which makes such important things happen in the universe, right? So it's capillary action, or sometimes we call it as capillary rise or capillarity, right? There are different ways. So class, I will request you all to please jot this down in your copies. Once you do, raise your hands so that we can move ahead. Yes, class, get going. Okay, so let me see. Yes, all have raised hands. Thank you, class. Let's begin the chapter. Okay, so let me talk first of all to all of you. Let's start with Anukriti. Anukriti, are you being able to recall these terms from what you have read in the past? Yes. Tell us.
Yes, sir. Yes.
Anything else that comes to your mind when you read these terms? Any explanation, any definition you want to talk about? Yes, Anukriti.
So the stress strain graph and
The
mm,
stress and strain graph. Excellent, excellent. Absolutely. Yes. Anything else that comes to your mind? Any pictures that build in the mind?
venturi meter.
Venturi meter, orifice meter. Excellent, excellent. Yes, 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 yes. So when you read about the concept of Bernoulli's theorem, right, that is how, and the equation of continuity. So these two equations come under application when we are reading about Venturi meter. Very good. Venturi meter and orifice meter. These are the devices which are used to measure the liquid flow rate, right? And a lot more, right? Yeah. Anything else that comes to your mind? Let's start with Karuna. Yes, Karuna. Karuna, you there?
Mm,
Yes, yes.
Please can you, one request to all of you, kindly make sure that you're close to your microphone, because sometimes your voice may not be that clear to everyone, right? So yeah, thank you. Yes, yes, go ahead.
So I think it's this much only.
Okay.
I don't remember anything else.
No worries, it's okay. Yeah. Atul, anything else that you, any picture that comes to your mind, anything you want to share with the class? Yes.
No, sir. Nothing new, sir.
Okay, great. No worries. Right. So class, let's start off. Let's start off with the session. Okay. So here is the beginning of it, right? So in this chapter, there is a lot that you study about. There is a lot that you study about, right? And I'll also give you all some important formulas that will be super helpful when you're solving this chapter along with the concepts and the numericals. Okay. So let's start off. Let's begin. So here we start, right? First is elastic behavior, right? So what is elastic behavior? Elastic behavior is a very beautiful concept. Now all of us read about plastics, right? Atul, what is, do you, can you just try to figure out or try to maybe recall that what should be a difference between, what should be difference between elastic and plastic quantities, something which is elastic and something which is plastic, what should be a major difference between them? Yes, Atul.
Uh, Elastic bodies regain their original shape and size.
And what about plastic?
Retain their and plastic bodies are unable to retain their original shape and size.
Absolutely, absolutely correct, right? So, class, this is how we all need to relate things and remember. You know, sometimes you may not very clearly or very vividly remember some definitions. So just connect them to something. So let's say I want to recall what is elastic. So I'll connect it to what is plastic, right? So take a plastic polythene. Of course, don't do this, but just for quoting, right? Take a plastic. If you have a plastic polythene, right? And you try to stretch it from all sides, try to stretch it from all sides and make it bigger. Karuna, can you tell me, let's say I have, let's say I had a piece of plastic polythene, right? I took the polythene, right? I took the polythene and I stretched it from all sides. I stretched it from all sides. Tell me one thing, once its size grows bigger, one, once the size of the plastic polythene grows bigger, will you be able to revert it back? Is this transition possible?
No, sir.
No, right? So this kind of materials, right? The materials which when are exposed to or when are given some kind of deforming forces. So these are called as deforming forces. So forces which tend to deform the uh, kind of deform the shape of the body, right? So if the shape of the body is being deformed and it is being converted into a new shape, right? The shape is being changed. When those forces are removed, when those forces are removed, if the body does not return back to gaining its original shape, right? Then such a body is called as plastic, which does not regain its shape on removing the deformed forces, right? Does not regain its shape. Correct? Whereas now it becomes so easy to define elastic quantities, the quantities tend to tend to regain their original shape, their original shape, the quantities which or the things which tend to regain their original shape after removal of, this is very important, right? After removal of deforming forces. Deforming forces. Deforming forces. Okay. Yes. So I hope this concept is now into your minds, right? Great. Now let us transit to the next part of it, right? Now, once we have understood that how there are different kind of elastic behavior shown by the body, let us revise the term stress. We all know that stress, we all have read this, stress is nothing but this now as we saw this, there is a deforming force on the body. What should be the case with the elastic body? What should be the case with elastic body? Here also, let's say this is the body. Okay, now I try to deform the body. See, deforming forces are forces which tend to change the shape of the body, deform it, right? Changing its form. So now let's say the shape of the body is changed. It is in a new shape, or maybe let's say its dimensions have altered, right? Its length and breadth have altered, right? Now what happens is its shape is it's of a bigger surface area. Let's say this, okay? Now, what happens is these were some forces that you were applying in order to make sure its size increases. Now, suppose you withdraw these forces. Class, listen very clearly. I am saying, suppose you withdraw these forces. Suppose you withdraw these forces, right? The forces are withdrawn. Which forces? Deforming forces. So, when deforming forces are withdrawn, when deforming forces are withdrawn, right, this will lead to deforming forces getting withdrawn will lead to restoring forces coming into action. So although restoring forces were also into action before, but now they are no longer balanced by deforming forces. So these restoring forces will make sure that the body will shrink back and attain its original shape, right? Right? So see what have happened. We had some deforming forces, right, which deformed the body. Then we also had some restoring forces, So these were restoring forces, restoring forces. So what was the work of these restoring forces? To restore the body back into its original position, right? Or to be very precise, back to into its original shape. Okay. Now see here, stress, right? So stress is given by these restoring forces. These restoring forces being applied by the molecules of the body, right, per unit area, per unit area. So kindly write it down. And it is which area? It is cross section area, CS, cross section area. Okay, this cross section area, CSA. Some people also call it CSA, cross section area, right? Right. So please take this down, right? Of course, you all remember that unit of force is Newton, right? Unit of area is meter square. So the unit of stress will be Newton per meter square, right? We have learnt about dimensions, right? Try recalling the dimensions of force. Dimensions of force are MLT minus 2, right? And then this is length. So it will again be L minus 2. So this will give you ML minus 1, T minus 2, right? So this is what stress is. Now even the stress is divided into three parts. Three kinds of stresses are observed. Very simple, very easy to understand. Based upon the dimensions it's working in, right? So when I say dimensions, I mean length, breadth, height, everything, right? So first one is called as longitudinal stress. Write it down. First one is called as longitudinal stress. Maybe I need not write the word stress again. It will save my space, right? So longitudinal stress is, it's basically the normal component of force. Class, I hope you all remember from the classes before that there is something called as a component of a force. There's something called as a component of a force, right? That means it can be normal or tangential component. There are two components that can happen, normal and tangential component, right? So normal force per unit area, normal force per unit area is called as longitudinal stress, is called as longitudinal stress. So when I say this, how do you diagrammatically represent this? Let's say this is the area, right? So the force that I'm talking about has to be acting perpendicular to this area. So let's say I'll draw even a better surface. Let's say this way, right? So yeah. So this is, let's say, a rod, right? Now I am drawing, see here, this surface. This is called as the cross section surface area, this one, right? Let's say this is circular in shape, right? So when you see it from in front, when you see it from front, you might be able to see this kind of area, right? Spherical surface area. Now if you apply a force which is perpendicular to this area, right? Such a force will be called as normal force. Such a force is called as normal force. And the stress will be called, the stress generated because of such a force will be called as longitudinal stress, will be called as longitudinal stress, right? Correct? Now it can be of two types again. One can be called as tensile and the other can be called as compressive. So tensile means which has a tendency to make the object expand, right? And compressive, obviously, which has the tendency to make the object shrink in size, right? So this longitudinal stress is of two types, tensile and compressive, right? Then next one is volumetric stress. Volumetric stress. So volumetric stress, name makes it clear, right? The force, right, which is again acting per unit area, but this force is acting on its volume. This force is acting on its volume, right? Somehow this force is acting on its volume. We'll see more about it very soon. Let's say I'll draw a sphere here, okay? Let's say I draw a sphere here. So this particular sphere may have some force which is acting per unit area of this sphere, right? Again, per unit area of this sphere, right? So this sphere will said to have been exposed to volumetric stress, right? So in essence, this force which is being applied on the volume of the sphere will make sure that the volume of the sphere increases. Volume of the sphere increases or decreases, again depends upon what kind of force we are applying, right? Are you clear? So it depends upon the fact that what is my force tending to do. If my force is leading to an increase in the length, it might be called as longitudinal stress. If the force is trying to, so that force per unit area will be called as longitudinal stress. If the force is trying to cause a change in the volume, then that force may be called as, that force per unit area might be called as volumetric stress, right? So again, this is force acting on the volume per unit area, right? Again, the unit will remain same. The dimension will remain same, right? Just the definition is changing based upon where is this force acting and what is the end result of the force. Class, remember what is the end result of the force. So here the end result is causing the length to get increased. Here the end result is causing the volume to get changed, correct? Now, Next one is shearing or tangential stress. Next one is shearing, or sometimes we call it even shear stress. Shear stress, right? Or tangential stress. The name of it makes it clear, right? Suppose here the value of it, here the value of it will be given as tangential force per unit area. Tangential force per unit area, right? So to give you an example, let's say you have a cube. Let's say you have a cube here, right? What you do is you apply some force on its surface, on its, let's say the upper surface over here. You apply a force this way, right? And the cube turns itself, see here how, this way, into a parallelopiped. So initially it was a cuboid and now it has turned into a parallelopiped. See here, this front surface which was looking like a square now looks like a parallelogram, right? So this is how a tangential force works, right? It makes every side turn through some angle. It makes every side turn through some angle, right? And that force which is acting on the surface to do so is called as tangential force, right? Or maybe there is a lot of force acting, right? We are considering only the tangential component of it, which is causing the shear stress, Clear? A lot of discussion, a lot of information we have got now about different kinds of stress, right? Class would like to know if this concept of stress, if this concept of elastic and plastic nature of the bodies and the unit, etc., are clear at your end. Because this is a revision, right? I hope you are very quickly able to catch these terms. Yes. Yes, class. If yes, please raise hand. Great. Any doubts? Anyone? Let me know. Atul, Karuna, Anukriti, anything you want to ask? Let me know if yes. Okay, great. So if it's clear, we'll see the next part of it. So next one is, we will read the term called strain. The way we read stress, now we are reading strain. What is strain? See here. So very simple, right? Whenever you are exposing a body to some kind of stress, so there is going to be some change in dimension, right? Now, because of that change in dimension, we consider a ratio. See here. Let's see how that ratio is different in case of a long wire, maybe a volumetric object, right? Or maybe different because of the tangential stress, right? So you have three kinds of strains. Like stress was of three types. Because of different types of stress, longitudinal, volumetric, and shear, you have three types of strain, again with the same name: longitudinal, right? Volumetric, and you would have guessed it right, shear strain. So you have three types of strain happening. Strain is the ratio. If you want to define strain in general terms, strain will be the change in dimension, right? It is the change in dimension by the original dimension. Change in dimension upon original dimension. Right? Change in dimension upon original dimension is the value of strain. Of course, when you're talking about some long rod, right, to which on both sides you applied same force F, this force resulted in some change in its length, right? then we call this particular change which happened, right? This particular change from both sides which happened, the total value of it, let's say that is delta L. That is delta L. The total value of the net change, let's say from here it expanded by delta L1, here it expanded by delta L2. So the total value delta L1 plus delta L2 is equal to delta L. Total change in length upon its initial length. Let's say that initial length was L, right? So you have delta L by L called as longitudinal strain. It's called as longitudinal strain. Similarly, let's say the volume of an object. Let's say the volume of an object was initially V, right? Now you applied some force on all sides because of which it has a larger volume. Let's say initially the volume was V, now it's V plus delta V. So how will volumetric strain be defined? Change in volume, right? Delta V upon V. Easy to understand. Now, when you're talking about shear stress class, you have to be careful. Why? Because here, try recalling, what did we do? We had a cube or a cuboid, right? And we led to, so just a second class. Yeah. So we have a cuboid, correct? And what are we doing to this cuboid? We are applying a force on its surface. Let's say this is how the cuboid was, right? We applied some force on its surface and it became something like this. This surface, the top surface, this one here. We applied some force here, right? And it changed. How did it change? See here. So, correct? Now, similar way on the other side. See, it has become a parallelopiped, right? I'm trying to tell you, I hope you all are able to figure this out by the diagram. It has almost turned into a parallelopiped. That is now its front surface, which was initially looking like a rectangle, that is now looking like a parallelogram. So suppose we have this length, right? This was the original shape, or I will turn it around. Let's say, okay. So let's say this is the new shape, right? First I'll draw this. So this is the new shape, right? Now this angle by which it has turned, this one. I'll draw it here clearly. This one, this angle, right? The angle by which the front face has tilted, right? Let's say that angle is theta. Right? And let's say this length is x, right? And this height is h, right? And this angle is theta. So I'm redrawing this triangle here. See, I'm redrawing this triangle here. Correct? Now I'm talking about this angle, right? This angle is theta. This is x. This is h. So we have shear strain. We have shear strain is given by this value x by h, which can also be written as tan theta. You must have clearly realized that strain has no units because it is a ratio. It is a ratio of quantities having same units, having same dimensions. Therefore, strain has no units. Remember, strain has no units. Correct? Coming to the next part. I hope this is clear with everyone. Let me know if you have any queries once we complete a sub part of it. So now we are talking about, let's say, stress and strain relationship, right? Which I think Anukriti pointed out that, sir, there was something that we read. What was it? Arey bhai, there was something like stress and strain relationship, or the graph between stress and strain. Class, I hope you all are understanding one very beautiful fact. Because of stress, strain is induced. Because I'm applying a force to the body, right, on both sides, equal force F, right, then we have some expansion in its dimensions, and that is how we define the concept of strain. So had there been no stress, had there been no force per unit area, there wouldn't have been any strain developed. It's very important to note this. Stress causes strain to happen. No stress, no strain. Very important. Clear? No stress, no strain. One very another important fact, right? So you can take this as a note maybe. No stress, no strain. Only stress causes strain to happen, right? So you can write this here as a note that stress leads to strain, right? This is one note. I want you all to note down something else also. Now, what's the second note? So Atul, can you answer this? Tell me, I have two rods, okay? I have two rods. So I'll draw them here. This is one, right? This is another rod. I'll draw it with another color. Let's say red. So let's say I have two rods. One is yellow, the other is orange in color. Now what I do is I apply some force on both the rods. On the first rod, I just apply force on one side, whereas on the second rod, I apply force on both sides. Atul, tell me what should be the difference? How will the rod react to it?
Uh,
Rod A and rod B. In the first case, what will happen? Will the rod expand?
I think in the
I think there is some network issue. Atul, try once again.
first case,
In first case, will the rod expand? Or will it start moving with some acceleration? That's all right.
the
That's all right. I think there is some network issue. No worries, no issues. Let's take the answer from Karuna.
problem.
So is my voice now clear again? Everyone, Atul, Karuna,
Yes, sir. Yes, sir.
is everyone able to clearly hear me? Anukriti?
Yes, sir.
Anukriti, I think your mic is very much far away from where you are sitting. Can you please be a little closer to your mic? Your voice is very weak when I'm hearing it. Hello?
Yes, sir.
All right, all right. Yeah. Thank you, Anukriti. Thank you. So let's continue from where we were, what we were doing, right? So we were talking about, I think, strain, right? Three different kinds of strain we were seeing. And before that, after that, I told you a relation that only when there is a stress, there is going to be a strain, right? We saw a note that only because of stress can there be strain. Stress leads to strain. This was one thing. Second, Atul, now can you try? We have two rods, right? First rod, and here is the second rod. Now you want to tell me, if I apply just force F on the first rod, whereas I apply two forces on the second rod, what will happen? What will happen to the rod A and rod B?
I think the length of the rod A will not increase, sir, as
Right.
force is only applied on one end.
Okay. So Atul is saying that, sir, rod A length will not increase, rather it will start moving. Why will it move? Because this person called Newton has told me that he has told us that force is equal to mass into acceleration. So whenever there is force, body will have some acceleration. So initially, let's say it was not moving, right? Its velocity was zero. So because of acceleration, what does acceleration do? It changes velocity, right? Acceleration is change of the velocity per unit time. So the body will start moving in the case one. Whereas what will happen in case two? Yes, let us hear the answer from Karuna. Yeah, Karuna, try and let me know what will happen in case B.
So if the force on both ends are equal, then the size will be increased.
Right? So the rod gets elongated rather than moving. It's very important to understand that when I'm writing stress is equal to force per unit area, right? So in reality, the net force acting on the body is zero. See, force is acting from both sides, right? Force is acting from both sides. It's also acting in the left direction. It's also acting in the right direction. So the net force is still zero. Net force is zero. So when I write this force, F, right, it means this one of the forces out of the two forces which are acting in both directions, is one of the forces is F, right? I hope you are clear with this understanding, right? I hope the concept is now clear. This is the working. This is the concept that force F is acting on both sides of the body in order to make sure the body gets elongated, right? So what is the response of the second body? The response of the second body is that it gets elongated. It gets elongated when we have a tensile force acting. See, do you remember tensile stress and compressive stress? So tensile stress tends to elongate the body, whereas compressive stress tries to compress the body, right? I hope it's clear now, right? Karuna, is it clear?
Yes, sir. Yes, sir.
Atul, is the concept clear?
Yes, sir.
Anukriti, tell me, is the concept clear to you now?
Yes, sir.
Okay. Any queries, anyone? Let me know. Okay, great. So now the next thing that we are reading is the stress strain relationship. So when you recall your class 11th, you had read that in stress strain relationship, there are different ways that different phases, right? So let's say I'm representing stress on the y-axis and strain on the x-axis. Initially, what happens is both are directly proportional to each other. Both are directly proportional to each other initially. Later, what happens is that proportionality is not followed for some time. Correct? Now, what do we call these regions? The first region, when they are proportional to each other, let us say A to B, that AB zone is called as proportional limit. So in fact, B will be called as, so AB is proportional zone and B is called as proportional limit. B is called as proportional limit, or even better, I will name the point, this one as origin and this one as A. So we'll have A is called as proportional limit. It is that limit, right? It is that limit until which proportionality relationship, this is that limit until which proportionality relationship was followed between stress and strain. Stress and strain following a proportionality relationship from O to A. So A will be called as proportionality limit, right? Or proportional limit. Proportional limit, correct? Similarly, from A until the next point, let's say, let's call this B, right? There is no longer proportional relationship, but the relationship is elastic yet. What do I mean elastic yet? I'll tell you. So note down B is equal to elastic limit. Elastic means if the body is undergoing a change, right, in its dimensions, that is its length, volume, whatever, right, or that angle theta we had seen. So whenever the body is undergoing some kind of change in its dimension until the point B, elastic means the body can return via same path, that is the same graph. The body will return via same graph. That means as soon as I withdraw the stress, see, the stress was increasing, and the strain was increasing. See, the strain was increasing, correct? See here, everyone. Here, initially somewhere stress will start from 0. It will reach some point. That time strain will have some value. Similarly, after some more time, stress will have some value, strain will have some value, right? Similarly, after some more time, stress will have some value, strain will have some value, correct? So this is how stress and strain are increasing up till a limit. Now, if I, let's say, withdraw the stress, I take away the stress, I again start reducing it, right? So when I start reducing it again, the strain will also start reducing, right? And the body will start coming back to its normal position, normal shape, right? So, or the original shape. So such limit, this can happen only till a limit. That limit is called as elastic limit. Try recalling what was elastic. Try recalling what was elastic. I had told that elastic means a body which can regain its original shape. So until limit B, right? Until limit B, until here, the body can regain its shape. The body can regain its shape. The body can regain its shape. Right? Now, next part of it is called as plastic region. Next part of it is called as plastic region, right? And more importantly, we should understand that here the particle is showing after this something called as plastic behavior. Plastic means after this, whatever expansion is there, the object is not able to regain its original shape. The object is not able to regain its original shape, right? There is some point which is called as breaking stress. Some point which is called as breaking stress. That means this is that point, it will lie in the plastic zone, right? So this was the elastic zone, first one until B. This was elastic zone. Until here, the object was allowed to go back to its original position. And this next one is called as plastic zone. So here, the object cannot go back to its original shape. There is one point here, which is called as breaking stress. Here, this point. Or at this point, this is the maximum stress which the object can bear. This is the maximum stress that the object can bear. Here, if the object could not bear it, it will tend to break the object, right? And finally, when it tends to break the object, it will be at a point called as fracture point. It will be at a point called as fracture point. And this topmost point is called as breaking stress. Here, the stress at this point is called as breaking stress. And let's say we name these points as C and D. C and D, correct? So kindly note this down, class. All right. So class, we have understood today in today's class what is elastic behavior, what is stress, the different kind of stress that develop, the formula for each, different kinds of strain, some important understanding about stress and strain, right? And the stress strain relationship. in the coming classes, we'll continue with the syllabus which was told. Thank you everyone. In the next class, let's try to see the other relations and quickly solve as many problems as we can, right? I'll send you the problems, I'll send you the question, we'll solve them, and we will keep going, right? So thank you everyone for being a part of the class. Let's catch up in the evening in the practice session where we'll try to complete the syllabus and the like the main key points of the syllabus and the important practice problems. Thank you everyone. Thanks a lot. Thank you.
Thank you, sir.
Thank you very
Thank you,
much.
sir.
Thank you. Thank you. Thank you very much.
Thank you, sir.
Thanks a lot, Atul. Thank you.